Hello students, welcome to this lecture on triangles. So in this lecture, we will discuss similarity of triangles. Okay, so let's get started. So we have studied in our previous lecture similarity of two polygons. Okay, so you can say a triangle as a polygon. What can you say about the similarity of two triangles? You may recall that triangle is also a polygon. So we can state the same condition for the similarity of two triangles. Okay. So for two polygon, there we have seen the definition of similarity. That case, two conditions must be held. Okay. So number one, their corresponding angles are equal and their corresponding sides are in the same ratio. Okay. So the same condition for the similarity of two triangles. That is, two triangles are similar if their corresponding angles are equal and their corresponding sides are in the same ratio. Okay, or proportion. So here note it down. If corresponding angles of two triangles are equal. Okay, so suppose you have two triangles and their corresponding angles are equal. Then what can you say about two triangles whose corresponding angles are same? Okay, so these two triangles are known as equiangular triangle. Equi means same. Okay, so they are known as equiangular triangles. So a famous Greek mathematician Thales gave an important truth relating to two equiangular triangles, which is as follows: the ratio of any two corresponding sides in two equiangular triangles is always the same. Okay, so this important truth is very important in triangles chapter. Okay, so the ratio of any corresponding sides in two equiangular triangles means if we have two triangles whose the corresponding angles are same, okay, then the ratio of two corresponding sides in these two equiangular triangles is always the same. Okay, so it is believed that he had used a result that is known as basic proportionality theorem. Okay, that is also known as Thales theorem for the same. So to understand the basic proportionality theorem, here we'll perform the following activity. Okay, so if we perform the following activity, then this will help you to understand the basic proportionality theorem. Okay, so let us perform the activity. So here activity 2. Here we draw any angle x, a, y, and one arm ax. Mark here some points. Say 5 points here we mark, like P, Q, D, R, B, X. Okay. So here we mark these points such that this length of this portion AP, this is equal to length of this portion PQ, and this is equal to QD, and this is equal to DR, and this is equal to RB. Okay, so such a way we mark these points P, Q, D, R, and B. And now through B, here draw any line intersecting AY at C point. Okay, so you can see this figure. This figure is 6.9 figure. Okay, so if you see this figure, here basically we mark some point in arm AX as PQDRB, so that AP, this is equal to PQ, this is equal to QD, and this is equal to DR, and this is equal to RB. Okay, And now through B here, now through B point, draw any intersecting line. Okay, so here we draw this line which actually intersecting arm AY at C. So at C point. So now also through the point D, here you see, also through the point D, here draw any line intersecting AY at E. Okay, and draw a line parallel to BC to intersecting AC at E. And do you observe from your construction that this ratio AD, this ratio AD divided by DB, okay, is divided by DB. This is equal to 3 by 2. Okay, so you can measure AE and EC. And what about AE over EC? Okay, so what about you can say the ratio AE and EC. Okay, so if you observe that, then this ratio AE over EC is also equal to 3 by 2. Okay, so from the previous figure, you can measure AE and EC, and you can find the ratio AE by EC, that is equal to 3 by 2. Okay, so thus you can see that from the triangle ABC, from this triangle ABC. Okay, so from this triangle ABC, here this is DE. DE is parallel to BC. Okay, so from this triangle DE, this side is parallel to BC, and here the ratio AD over DB, this is equal to AE over EC. Since we can observe from our construction AD over DB, this is equal to 3 by 2. Okay, and if we measure AE and EC, then we can find the ratio AE over EC, that is equal to also 3 by 2. Okay, so from this triangle ABC, here DE is parallel to BC and AD over DB, this is equal to AE over EC. Okay, so now question, is it a coincidence? But our answer is no, this is not a coincidence. It is due to following theorem that is known as the basic proportionality theorem. Okay, so here if we have a triangle, okay, and if one side is parallel to another side, okay, then you can find this ratio AD over DB, this is equal to AE over EC, and this is known as the basic proportionality theorem. Okay, now here we see an important theorem. Okay, so this theorem stated to us, if a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, the other two sides are divided in the same ratio. Okay, so if we draw a line that is actually parallel to one side of the triangle which intersect the other two sides in distinct points, okay, then the other two sides are divided in the same ratio. So let us prove it. So here we will prove this. Okay, so we are given this triangle ABC. Okay, so in which a line to side BC, here in this side BC, here a line parallel to BC, okay, and intersection other two sides AB and AC, at D and point E respectively. So you can observe this figure. Here we have this triangle, okay, and in which a line is parallel to this side, okay, and intersecting the other two sides AB and AC at point D and E. Okay, so here we need to prove that AD over DB, this is equal to AE over EC. Okay, so we need to prove AD over DB, this is equal to AE over EC. So let us join BE and CD. So here in this figure, here we join BE and DC, CD. Okay, and then draw DM, which is actually perpendicular to AC. Okay, so this actually DM, this is perpendicular to AC, and also EN, this is perpendicular to AB. That means this angle is 90 degree and this angle is 90 degree. So DM is perpendicular to AC and EN, this is perpendicular to AB. Okay, so now area, we know area of the triangle. So for an area of the triangle, that is actually equal to half into base into height. Okay, so now from this triangle ADE, this triangle, from this triangle here, the height is AD and the base is DE. So here the area of this triangle is equal to half AD times EN. And if you recall from class 9, there we denoted the area of the triangle as AR of that. Okay, so here triangle AD, area of this triangle AD is denoted as AR of ADE. Now, so area of ADE, this is equal to half of AD into EN, where AD is height of this triangle and the base is EN. And similarly, you can find the area of ABDE from this figure. So here this triangle BDE, this triangle. Okay, so area of this triangle is basically equal to half into DB into EN. Okay, and similarly area of ADE. So if you observe the figure, then you will get a triangle ADE. Okay, and the area of that triangle ADE, this is equal to half into AE into DM, where A is height and DM is base of that of this triangle ADE. Okay, and area of DEC, this is equal to half into EC into DM. Okay, here the height is EC and the base is DM. Okay, so now therefore area of ADE divided by area of BDE, this is equal to half times AD into EN divided by half times DB into EN. Okay, so here EN half will cancel out. Okay, and we get this is as AD over DB. So here the ratio of area ADE and area BDE, this is equal to AD over DB. And naming this equation number 1. And now if we find the ratio of area ADE and area DEC, that is equal to half into AE into DM divided by half into EC into DM. Okay, and here you can cancel half and DM and you get this is equal to AE over EC. Okay, so the ratio of area ADE divided by area of DEC, this is equal to AE over EC, and naming this equation number 2. Okay, so now note that triangle BDE and triangle DEC are on the same base DE. Okay, so you can observe the figure here, triangle BDE and triangle ADE. Here the base actually same, that is DE. Okay, so for these two triangles the base are same. Okay, so and between the same parallels BC and DE. So basically area of BDE, this triangle, this is equal to area of DEC, and naming this equation number 3. Okay, so we get this relationship, area of BDE, this is equal to area of DEC. And now if we compare 1 2 3, equation 1 2 3, so therefore from equation 1 2 3 we have the ratio AD over DB, this is equal to AE over EC. Okay, so here basically if we use the equation 1 2 and 3, then we get this ratio. Okay, so AD over DB, that is equal to AE over EC. Basically we need to prove this ratio are equal. Okay, so here we prove this theorem. So now question, is the converse of this theorem also true? So here for proving converse of this theorem is also true, so you can see appendix 1. Okay, and here to examine this, here we let us perform the following activity. Okay, so in our next slide we'll perform the following activity, and by that activity we can say the converse of this theorem, that is converse of basic proportionality theorem is also true. Okay, so here we have activity 3. So draw an angle here XAY on your notebook and one ray AX, and here mark point B1, B2, B3, B4, B5, okay, and B, such that AB1, this is equal to B1, B2, this is equal to B2, B3, this is equal to B3, B4, and this is equal to B4, B. Okay, and similarly one ray AY and mark point C1, C2, C3, C4 and C, such that AC1, this is equal to C1, C2, this is equal to C2, C3, and this is equal to C3, C4, and this is equal to C4, C. Okay, and now if we join B1 and C1 and B and C, that is shown in figure 6.11. Okay, so here basically we draw an angle XAY. Okay, and here in ray AX mark some point B1, B2, B3, B4 and B, such that AB1, this is equal to B1, B2, this is equal to B2, B3, this is equal to B3, B4, and this is equal to B4, B. Okay, and similarly one ray AY, here we mark some points C1, C2, C3, C4 and C, such that AC1, this is equal to C1, C2, this is equal to C2, C3, and this is equal to C3, C4, and this is equal to C4, C. And then we join B1, C1 and B and C. Okay, so now here note that this ratio AB1 and B1B, that is AB1 divided by B1B, this is equal to AC1 by C1C. Okay, so if we here compare this ratio, AB1, this is divided by B1B, and this is actually equal to AC1 divided by C1C2. Okay, and C1C, that is equal to 1 by 4. These are equal since this is equal to 1 by 4 and this ratio is equal to also 1 by 4. Okay, so that is why AB1 by B1B, this is equal to AC1 by C1C. And you can also see that line lines B1C1 and BC are parallel to each other. Okay, so this line B1C1 and BC, they're actually parallel to each other. Okay, so that is B1C1 is parallel to BC. Similarly, by joining B2C2, B3C3 and B4C4, you can see that this ratio AB2 divided by B2B, this is equal to AC2 by C2C. These are equal since they are 1 equal to 2 by 3. Okay, so this is equal to 2 by 3. This is equal to 2 by 3. Okay, and this is equal to also 2 by 3. Okay, that is why they are equal. And this B2C2, this is parallel to BC. Okay, and naming this equation number 2. And here AB3 divided by B3B, this is equal to AC3 divided by C3C, since both are equal to 3 by 2. Okay, and here the line B3C3, this is parallel to BC. Okay, and AB4, this is divided by B4B, this is equal to AC4 divided by C4C. They are both equal since these two ratios are same as they are equal to 4 by 1. Okay, and here the line B4C4, this is parallel to line BC. Okay, so here from equation 1, 2, 3 and 4, it can be observed that if a line divides two sides of a triangle in the same ratio, okay, then the line is parallel to the third side. So here from this equation, it can be observed that if a line divides two sides of a triangle in the same ratio, then the line is actually parallel to the third side. Okay, so you can repeat this activity by drawing any angle XAY of different measure, okay, and taking any number of equal parts, one arms AX and AY. Okay, so each time you will arrive at the same result. Thus we obtain the following theorem, which is the converse of the theorem 6.1. Okay, so by this activity here we prove the converse of the theorem 6.1. okay, so converse of the theorem 6.1 is also true. Okay, so here from this activity we observe this thing: if a line divides two sides of a triangle in the same ratio, then the line is parallel to the other third side. Okay, so this is actually the converse of the theorem 6.1. and now theorem 6.2. okay, so this theorem said to us, if a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. Okay, so if a line divides any two sides of a triangle, so here divides a line DE any two sides AB and AC in the same ratio, okay, then this line is actually parallel to the third side, that is BC. okay, this line is parallel to BC. So this theorem said to us, if a line, suppose we take this line DE, which is actually intersects, okay, at side AB at D and AC at E. Okay, so here basically this stated to us, if a line divides two sides of a triangle in the same ratio, okay, then the line is actually parallel to other side. So this theorem can be proved by taking a line DE. So here by taking this triangle ABC. Okay, and if we take a line DE such that this ratio AD over DB, this is equal to AE over EC. Okay, so this line divides these two lines and the same ratio. Okay, then, and assuming that DE is not parallel to BC, so here we assume DE is not parallel to BC, but we need to prove that DE is actually parallel to BC. Okay, so here we basically take opposite of the adjunctions. Okay, so if D is not parallel to BC, and draw a line DE dash. Okay, so here we draw this line DE dash, which is actually parallel to BC. Okay, so AD over DB, this ratio, this is equal to AE dash over E dash C. Okay, since they are parallels from the previous theorem, here we can say this ratio are equal. AD over DB, this is equal to AE dash over E dash C, and therefore AE over EC, here this AD over DB, this is equal to AE dash over E dash C. Okay, and therefore here AE over EC, this is equal to this ratio AE over EC, this ratio is equal to AE dash over E dash C. Okay, so adding 1 to both sides of the above, so you can see that E and E dash must coincide. Okay, so here from this ratio AE over EC, this is equal to AE dash over E dash C. This ratio actually implies to us that E and E dash, these 2 points are actually must coincide. So here we first assume that DE is not parallel to BC, but we assume here DE dash is parallel to BC. But here we get E and E dash, these 2 points must coincide. Okay, that is, here we actually, here this contradicts the fact that DE is not parallel to BC. Okay, that means DE, this is parallel to BC. Okay, so let us take some examples to illustrate the use of the above theorems. Okay, so here you will use the above theorems by taking some examples. So let us explore the examples. So here first example 1. So in this example, here it's said to us, if a line intersects the sides AB and AC of a triangle ABC at the D and E respectively. Okay, so we have this triangle ABC, and here a line, this line intersects the side AB and AC of this triangle ABC at D and E. Okay, and is parallel to BC. So this line D is parallel to the side BC, and here we have to prove that this ratio AD over DB, AD over AB, this is equal to AE over AC. So here you can observe this figure. So in this figure, we first draw a line which actually intersects the side AB at D point and AC at E point. And here we take this line as DE is parallel to BC. And here we have to prove that AD over AB, this is equal to AE over AC. Okay, so let us prove it. So here we have given D, this line is parallel to the side BC. So from the previous theorem 6.1, here we get this ratio are equal. Okay, so AD over DB, this is equal to AE over EC, or DB, this is equal DB over AD, this is equal to EC over AE. Okay, actually we take here the reciprocal of the above equation. Okay, so now if we add in both sides, if we add 1 in both sides, then we get DB over AD plus 1. This is equal to EC over AE plus 1. Okay, or actually DB plus AD, DB plus AD over AD, this is equal to EC plus AE over AE. Okay, and here DB plus AD, DB plus AD, this is basically equal to the side AB. Okay, and EC plus AE, this is equal to AC. That is AB over AD, this is equal to AC over AE. Okay, so AD over AB, AD over AB, this is equal to AE over AC. Okay, so this proved our this here we proved the examples 1 by using theorem 6.1. Okay, so here I stop this lecture. Thank you very much to all of you.